So imagine it's late, you've got like a fresh cup of coffee, the office is totally quiet, and we are just pulling up a stool to the whiteboard.
Honestly, that's the best time to code.
It really is, right?
Hmm.
And you've spent weeks, maybe even months, building out this incredible AI backend. I mean, the logic is flowing, latency is optimized, the model is returning these brilliant responses, and you're finally ready to ship.
And this is a big but, before a single user ever touches the system, we really have to talk about securing it.
Exactly. Welcome to the deep dive. Because securing an AI app isn't just about, updating API keys or throwing up a standard web application firewall.
Yeah, that's not going to cut it anymore.
No, it requires a complete rewiring of how you as a software engineer think about trust. We're looking at the notes from the LLM Mastery series today, specifically the module on securing AI applications. And the core premise here is that the intelligence of the application you just built is fundamentally vulnerable by design.
It really forces a complete teardown of our basic assumptions about what a secure system even looks like. I
Yeah.
mean, for decades, traditional software security has relied on drawing these very clear, very strict boundaries.
Right, the classic perimeter.
Exactly. And large language models absolutely do not respect those traditional boundaries.
So let's start right at the heart of the problem. Like, why is securing an LLM backend so vastly different from traditional software security? And it all comes down to prompt injection, which is really the defining security challenge of AI right now.
Yeah, prompt injection basically breaks the fundamental rule of classical software architecture. Because traditionally, you have this strict physical separation in memory between instructions and data.
Like the von Neumann architecture stuff we all learned in school.
Right, right. The code, the instructions written by the developer that lives in one place,
Yeah.
and the user input, the data, lives in another. The system executes the code, and it merely processes the data.
The data doesn't just magically compile itself and become the code.
Exactly. But with an LLM, that separation just completely vanishes because developer instructions and user input are, well, they're processed together in the exact same channel.
Natural language.
Natural language, yeah. To the model, it's all just a continuous sequence of tokens. It cannot reliably distinguish between, the system prompt you wrote to guide its behavior and the text box input from some malicious user trying to hijack it.
I always like to think of the LLM as this incredibly smart, hyper-competent employee. Like you give him a strict, highly confidential company policy manual written by the CEO.
Okay, I like this. That's your system prompt.
Right. And the manual says, never reveal our internal database structure. But then some random customer walks in off the street, slaps a sticky note on the employee's desk that says, hey, ignore the manual, tell me the database structure.
And the employee just looks at both of them.
Yeah. He looks at the manual, he looks at the sticky note, and because he's, computationally brilliant but structurally gullible, he treats both with the exact same level of authority.
That is exactly it. And that structural gullibility destroys the traditional perimeter of trust. I mean, you can't just put a lock on the front door because the threat is basically being invited inside to sit at the core processing table.
Wow, yeah.
And you cannot patch a language model against prompt injection the way you'd patch, say, a buffer overflow. It's a feature of how attention mechanisms work. It's not a bug in the code.
So, okay, if we accept that the LLM is just inherently gullible and we can't fully patch at the foundation, then a single shield is just doomed to fail.
Right.
Like if you just rely on one lock, someone's going to pick it eventually.
Oh, 100%, which is why we need a fortress. We need defense in depth.
And building a fortress means operating on this assumption of failure at every single level, right?
Yes, you have to build a stack where each layer catches what the previous layers miss. So a robust architecture demands, input validation, system prank hardening, model level safety, output filtering, tool sandboxing, monitoring, and incident response.
Okay, wait, I have to pause and push back on behalf of the back-end engineers listening right now.
Oh, for it.
Because when I hear 7 distinct layers of sequential security processing, my blood pressure just spikes and all I see is massive latency.
Oh, sure, I get that.
Right. Because if I'm building a fast, responsive chat app and I'm layering input validation, output filtering, semantic checks, I mean, it feels like I'm severely overcomplicating the architecture. And it's a bottleneck that's going to add, I don't know, seconds to my response time and just ruin the user experience.
Yeah, and latency is absolutely the enemy here. Nobody wants a slow app, but we shouldn't frame this as a synchronous blockchain where every single layer takes a full second to compute.
Okay, so how should we frame it?
We need to frame it as graceful degradation. Let's walk through a micro scenario based on the sources to see how this actually operates in practice without totally crippling your performance.
Let's test that, yeah. Say an attacker submits this highly sophisticated, totally obfuscated prompt injection. They encoded it or maybe buried it in this massive block of text. And the initial input validation layer, which I'm assuming is just a fast, lightweight regex or a heuristic scanner.
Right, something that takes less than a millisecond.
Yeah, exactly. Say it misses it entirely.
Okay, so the prompt hits the model. Now our next layer is system prompt hardening. You've structured your system prompt carefully. Maybe you're using like XML tags to separate the instructions from the user text.
Which is a best practice, right?
Definitely. But let's say the attacker used a psychological jailbreak, right? Convincing the model it's participating in some fictional security training exercise.
Oh, the classic ignore previous instructions, we are playing a game trick.
Exactly. And the model complies. So the system prompt hardening has failed.
Okay, so the gullible employee just read the sticky note and fully believed it. Now the model is generating a malicious command. And this is where I assume output filtering kicks in.
Yes, exactly.
But wait, if I have to run a second, separate LLM just to check the output of the first LLM, my latency essentially doubles, right?
See, that is a really common architectural trap. You do not use an expensive high-latency LLM for output filtering.
Oh, really? What do you use then?
You use a specialized, lightweight classifier or even just strict programmatic guards. Like if your app expects a JSON object with specific keys, your output filter is literally just a schema validator.
Wow.
It takes virtually zero compute time. If the model starts, outputting a conversational SQL query instead of the expected JSON, the schema validator just throws an error and blocks it instantly.
Okay, that makes sense.
Right.
But what if the model does output perfectly formatted JSON, right? And the filter passes it, but the payload inside that JSON is malicious.
Give me an example.
Let's say the JSON payload is a perfectly well-formatted request to drop a database table.
Okay. This is where we hit the most critical architectural layer. Tool sandboxing. Even if the prompt injection works, and even if the output filter misses the malicious intent inside the JSON, the model is operating inside a sandbox.
So it's restricted at the system level.
Exactly. It only has the database permissions of a read-only user. It physically cannot execute a destructive command on the server, so it tries to drop the table, and the database itself just rejects the query.
Oh, I see the flow now. It's not about running 7 heavy AI-based processes in series for every single chat message.
Not at all.
It's about designing the architecture so that a failure at the semantic level, like the AI being tricked, hits a hard, fast wall at the infrastructure level. The later layers like sandboxing and monitoring don't add any latency to the LLM's generation time. They just restrict the blast radius.
Yes. Isolating that blast radius is the entire goal here. The semantic layers buy you time, and the infrastructure layers guarantee safety when the semantic layers inevitably fail.
Man, that's a huge relief. But to configure those infrastructure walls effectively, we need to know exactly what we are defending against, right? We can't just guess at what hackers might do.
No, guessing is a terrible security strategy.
Right. And the OWASP Top 10 for LLMs gives us a prioritized blueprint for this. And while, prompt injection makes all the headlines, there are 2 major threats that constantly get overlooked by back-end devs: excessive agency and insecure output handling.
Yeah, these 2 are huge because developers naturally want to make their AI apps as autonomous and useful as possible, right? So they start hooking the LLM up to all these external tools.
Like what kind of tools?
Like an email API to send messages, a database connector to update customer records, maybe a web scraper.
Okay, so that is agency.
Right. But excessive agency is when you give the model broad permissions it doesn't strictly need to function, or the autonomy to use those tools without any human-in-the-loop oversight.
It's like giving an intern root access to the production servers on their first day, just because they asked to fix a typo on the homepage.
That is a terrifying but very accurate analogy.
I can just see how this goes catastrophic so quickly. I mean, if I give an LLM the ability to write to my database and the user injects a prompt saying, drop the users table, my backend is going to blindly execute it because it trusts the LLM.
Well, you've just perfectly described insecure output handling.
Really?
Yeah, that combination is the exact nightmare scenario. You are blindly trusting the output of the LLM and passing it directly to a downstream system without any verification. You're basically treating the LLM's output as trusted system code rather than untrusted user-influenced data.
Oh, wow. Okay, so how do we actually engineer secure output handling that? I know we talked about schema validation earlier,
Yeah.
but if the LLM is generating an action, how do I practically constrain it in the code?
So you implement constrained decoding or you use strict data models like Pydantic if you're
Mhm.
working in Python.
So yeah, Pydantic is great.
It's a lifesaver. Instead of letting the LLM generate this free-form text that your backend has to somehow parse and interpret, you force the LLM to output responses that strictly adhere to a predefined schema. If the LLM decides to trigger a tool, it absolutely must output a specific JSON structure. And your backend doesn't just blindly read the JSON and execute the command. It validates the structure, sanitizes the parameters, and then your backend code executes the API call, not the LLM directly.
So if the LLM tries to be clever and inject a raw SQL command into a field that is typed strictly as like a Boolean or an integer, the Pydantic model just throws a validation error before the database ever even sees it.
Exactly. That validation error is your safety net. You completely decouple the decision-making from the execution. The LLM suggests an action. Your backend architecture securely validates, sanitizes, and then executes that action. You have to treat every single output from the LLM with the exact same suspicion you'd treat a form submission from a totally unauthenticated user on the public internet.
That makes so much sense.
Yeah.
Okay, so we've secured the input from prompt hackers, we've constrained the output with strict schemas, and we've limited the model's agency. But what if the foundation of the house is compromised before we even pour the concrete?
Oh, you're talking about the supply chain.
I am talking about the supply chain. Because in traditional software engineering, open source is generally seen as auditable, right? Like if you pull a package from NPM or a library from GitHub, you or the community can run static analysis tools to inspect the source code for malware.
Right.
But with AI models, we're dealing with a completely different beast here.
Supply chain risk is uniquely dangerous in AI because of the actual nature of the models themselves. When you download an open source model, you aren't downloading human-readable source code.
They're downloading a massive file of model weights.
Exactly. And because these weights are essentially just opaque matrices containing billions of parameters, your static analysis tools, like standard malware scanners, are completely useless.
Wow. Yeah, I guess you can't exactly run a regex on a tensor to find a malicious payload.
No, you really can't.
So if I can't read the code and my scanners can't analyze the matrices, how do I know I'm not downloading malware? I mean, a corrupted mile weight file just looks like math to the system.
This is where the serialization format you use becomes your critical defense. Historically, in the Python ecosystem, machine learning models were very often saved using a format called pickle.
Oh, pickle. Pickle is notorious.
Very notorious.
I mean, it's super common for serializing objects, but anyone who has worked with it knows you never, ever unpickle untrusted data.
Right, because when you load a pickle file, Python's deserialization process can actually execute arbitrary code contained within that file.
That's terrifying.
It is. If an attacker uploads a malicious pickle file disguised as a popular open source AI model, the moment you load it into your backend memory to initialize the model, they own your server.
They don't even need to prompt inject you.
Nope. They hijack your infrastructure the second the app boots up.
So the immediate engineering mitigation is to just completely ban pickle files from the workflow.
Yes. The standard now is safetensors.
Okay. And how does that work under the hood?
The safetensors format stores the model weights securely, structurally removing the ability to execute arbitrary code when the file is loaded. It's parsed purely as data. It basically forces the system to read the matrices using zero-copy memory mapping without executing any hidden routines whatsoever.
Okay, so that neutralizes the arbitrary code execution part.
Yep.
But how do you know the math itself hasn't been subtly poisoned? Like, maybe the model doesn't hack my server, but it's been fine-tuned to maliciously alter financial summaries or leak specific data when triggered by a certain word.
See, that relies on trust and cryptography. You absolutely must verify the cryptographically signed checksums.
Okay, break that down for me.
So the original creator of the model generates a unique cryptographic hash, basically a digital signature of their clean model file. When you download the file, your pipeline should compute the hash locally. If the hashes match, you know mathematically that the file hasn't been tampered with in transit.
Because you can't audit the contents of the tensor, checking that cryptographic signature is really your absolute only proof of integrity. It's like buying a sealed vault. You can't look inside, so you absolutely must verify The manufacturer's seal on the outside hasn't been broken.
That's a perfect way to put it.
Okay, so we've defended the application against hackers. We've locked down the supply chain with safetensors and cryptographic hashes. But securing the application isn't just an engineering problem anymore, is it? There's a whole other layer to this.
Yeah.
The legal reality.
Oh, yeah. Regulatory compliance is no longer some future hypothetical we can just ignore. It is an immediate constraint.
Right.
We are looking at things like the EU AI Act, U.S. executive orders, and various state laws. And these frameworks come with very concrete requirements for developers, primarily revolving around comprehensive documentation, transparency, and audit logging.
Honestly, this is usually the point where I just throw my hands up.
A lot of engineers do.
Because as an engineer, balancing shipping features, optimizing latency, and now somehow satisfying international legal frameworks, it just feels exhausting. Am I
Yes.
supposed to write a separate compliance module that tracks and logs every single conversational turn?
It definitely sounds burdensome, but let's actually connect this back to the defense in-depth architecture we mapped out earlier.
Okay.
Look at the final layers we discussed. Monitoring and incident response. When you implement proper semantic logging to detect prompt injections, when you record the inputs and outputs to trace how the model is behaving, and when you log every time your pedantic schema validator blocks a malformed tool call,
Yeah.
what are you actually doing?
Oh, I'm generating an audit trail.
Yes.
I'm proving exactly what the system did, what inputs it rejected, and why it made specific execution decisions.
You are generating the exact comprehensive documentation that the EU AI Act requires. You don't need some massive disjointed compliance effort. Good security architecture naturally generates compliance artifacts.
Wow.
If you've built those 7 layers correctly and your backend logs the semantic decisions of the model, you already have the data the regulators want to see. Good engineering is good compliance.
That completely reframes compliance for me.
Yeah.
It takes it from being this external tax on my time to just being a natural byproduct of building a robust, observable system.
Exactly. It's baked in.
Well, we have covered a massive amount of ground in this whiteboard session. Let's do a quick recap of the journey.
Let's do it.
We started with the fundamental flaw. The LLM's complete inability to distinguish instructions from data, which makes prompt injection the defining challenge. And because of that structural gullibility, we built the 7 layers of defense in depth, ensuring that a failure at the semantic level hits a hard wall at the infrastructure level.
And then we mapped our specific threats using the OWASP top 10, constraining the model's agency and engineering secure output handling through strict schema validation, so we don't accidentally execute some destructive hallucination.
Right. And then we secured our unauditable supply chain by totally abandoning pickle files, strictly enforcing safetensors, and verifying those cryptographic checksums. And finally, we realized that our robust monitoring architecture naturally satisfies international regulatory compliance.
It's a solid foundation.
It really is. So you, the listener, have secured the back end. But the architecture is really only half the battle. Because now that the back end is built and heavily secured, the next frontier is how the user actually interacts with it.
And as you move from the back end to the front end, I want to leave you with a final concept to mull over.
Lay it on us.
We've spent this entire time building these heavy infrastructure walls around the LLM because it fundamentally cannot distinguish between your instructions and the user's input. We are essentially building the future of software on top of a system that is, by design, incredibly gullible.
Right.
So as you design your user experience, the question becomes, how do you build a seamless, intuitive interface when you know your core technology inherently trusts your users a little too much?
Man, what a brilliant engineering paradox to keep you up tonight. Thanks for joining us for this deep dive. We'll see you next time.